Hello, everyone. I hope you had a great day so far. Let's start today's discussion. So far, the condition that we had for analyzing a system like a circuit and uh, 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 conducting DC analysis and DC measurement had a very fundamental assumption that our circuit is in a steady state and there is no deviation or variation or any change in our voltage or current. Now, today, we are going to talk about what would happen if the circuit is subjected to a change. For example, there would be like a sudden change in a voltage or in a current. And if so, how the circuit would react to such a behavior. Now, when we talked about the DC system, we always consider the capacitor and inductor. When we talked about the steady state in the DC system, we consider those two components as a component that would not affect our analysis. So we basically replace the inductor with a short circuit and a capacitor with an open circuit. Then we have a steady state DC. Now, when we have a transient, we cannot use such an assumption because both capacitor and inductor has a dynamic behavior, which, if you remember, the formula that connects or relates the current and the voltage for each of those components are basically differential integral formula. As you know, the current of a capacitor is the capacitance time the differential of the voltage across that capacitor. Okay? Same goes for the inductor. The voltage across the inductor is the inductance times the differential of the current going through that inductor. Now, you can fairly imagine that if we have a constant steady state DC, whatever you want to call it, current in an inductor, that VI over dt becomes zero. So the voltage across the inductor becomes zero, i.e. short circuit. Same analogy we can run on a capacitor and say, okay, if we have a constant voltage, a steady state DC voltage, then the dV over dt is zero. And therefore, the current passing through the capacitor is going to be zero, which we call it open circuit. Okay, now, when we don't have that a privilege of not having any differential, so there is a value for dV over dt for a capacitor or di over dt for inductor. Now we don't have a privilege of the open circuit, short circuit analysis. I assume you already passed the calculus and you are familiar with the ordinary differential equation. So you know the general standard representation of like a first order differential equation, which when we wanted to show it, the standard way is the tau first order derivative of our function plus our function is going to be the KSFT. The KSFT is the input, is the force that you apply to your system. Okay? And the X is whatever you want to measure or like analyze as an output. Now, whatever happened, now remember, the coefficient of X of t is 1. Now, if you have such an arrangement for your ordinary differential equation, for the first order differential equation, now the coefficients of the derivative, we call it tau or time constant. Okay, so what is the time constant? The definition of the time constant is going to be the amount of the time that it takes that x of t to reach 63% of the final value. Very good. It doesn't matter if it's increase or decrease. Okay, you can see that when it increase and the initial value is 0 and the final value is a certain amount of voltage, 63% of the value is going to be tau. And when it increase also 63% change, the duration that would happen, the time that would take that 63% change will be considered as a time constant. Now, you can imagine, as you can know, as you basically, I believe, know that where is that? When you have such a differential equation, you always have an exponential function in your output function. It is an exponential term in the function of the variable you are output. Are we clear on that? Do you remember the calculus and the differential equation? All right. Any question about that? No? If you have a question, you can go through the concept of the natural response and forced response. Search on that. This is the foundation of this kind of like discussion. Okay, now the premise of having an exponential function, it means we're never gonna reach the absolute final value. Okay, because we cannot reach infinity in time. So how we consider the steady state or the kind of like the finish line of a transient that you're talking about, the time or the value that we consider that, okay, from this value, now we are in a steady state, now the transient is finished, the change is finished, is 99% of the final value. So, for example, here, when we reach a value that is equal, like we reached a V1 that is equal to 99% of our final voltage, then we say, okay, we are good enough. This is good enough, and we reached this. Now transient is one. Now we can, if you don't have any changes, and like for example, it's constant. Now you can imagine that okay, it's a steady state, the capacitor is open circuit, the inductor is short. Are we good? Now, that 99% based on the equation that we have happens at the 5 tau. The duration, the time duration that it takes your circuit to reach that 99% is 5 time constant. Are we good? So this is basically the behavior, the dynamic behavior of any component that has a differential or integral dynamic when we talk about the relation between the current and voltage. Any question about what we discussed so far? No? You heard about this in circuit 1 too, right? Is that? Yeah. Okay, good. Now, if we have an RC, okay, a series RC circuit, you can simply run a KVL over your circuit, and you would find that your input voltage, if you run a KVL, your input voltage is going to be equal to the R times the current plus what? What is that? What is the voltage across the capacitor? Anyone remember? No, the current of the current of the capacitor was C dV over dt. Okay? So what is the voltage? It's going to be the integral of the current. Very good. So we are going to have 1 over C integral. You can basically, this is C dV over dt. So if you reverse that, it's going to be 1 over C, the integral of the current, dt. Are we good? We don't like the integral. So we take a derivative out of our equation. So now we have V input prime dV over dt equal to the R current prime differential, the first order differential of this one. And differentiating this integral is simply whatever is inside the integral. Are we good? Now you have a first order differential equation. In this specific case and the specific case that we have in our assignment, we always consider the input voltage as a step function. Okay? Now, anyone remember what is the differential of a step function? If you remember, talk like a little bit louder. Sorry? A Dirac? Yes. It's a delta Dirac, but there is a coefficient which is the initial condition. So the differential of a step function is the initial condition times delta Dirac. But here our initial condition in our situation in the assignment is 0. That means that V prime is 0. Are we good? Now, if that is 0, look at this one. That means the differential of the current is 1 over RC, the current itself. We already talked about that. The function that satisfies such a condition is exponential. Remember that? So we can easily find the time function, the function in time that describes the current. And now if you have the tau, which is the value of 1 over RC, okay? If you have the time of the tau, you can put that t inside your function and find the value of the current on that specific tau. Is that clear how we run the analysis? So for example, when you wanted to, like in the experiment, calculate the values of current or any voltages, which the function is a certain exponential function, okay? What you have to do is you have to calculate your time constant, okay? And then when you have the time variant function of your variable, you just put those values for time, 1 tau, 2 tau, all the way to 5 tau, and solve the value for the output. Is that clear? For example, if we have here, like let's say VC e to the power of minus t over tau plus VC, okay? Now, this is VC in infinity, so it's the final value of VC. The value of time in 1 tau is gonna be, this is minus V of C, the final value, minus the final value times e to the power of minus 1. This is gonna be 1 tau. we put t equal to 1 tau. Now, if it's 2 tau, it's going to be e to the power of minus 2. And we move forward. So you can calculate the values. Are we clear on that? Now, remember, we solve for current. If I ask you the voltage of the resistor, then you have to change the parameter to the voltage of the resistance, which is R times that is current. Are you good? So be careful about that values. Any questions so far about the RC? This one? Yeah. This is the solution for this differential equation. Okay, now, in our specific case, we consider that we have a step function that changes from 0 to 1, okay, in our time. So our final voltage, the value of the voltage in time infinity is going to be 1, okay? And our initial voltage in time 0 is going to be 0. So we basically, the general solution is if you run the integral and find the value for voltage, okay, is going to be the value in 0 minus the value in infinity, okay, times that exponential plus the value in infinity. Is that clear? Did I answer your question? Any question about that? This is just the mathematical derivation of the first order differential equation. You are familiar with that, right? Is there any question? Okay. Now, in your circuit, you wanted to like measure the time constant for an RC circuit in your lab assignment. So we have such a circuit in our lab with the RC series. And since we are in a transient mode, now the digital multimeter is not going to be helpful for us. So we have to use the oscilloscope. And what you're going to see is in the lab assignment, we want the transient behavior of the voltage across the capacitor. So we already talked about the calculation. Let's talk about the measure. How we can do the measurement? I already put the posted the video. Actually, I posted that before the semester starts, okay, about how you can work with the exact model oscilloscope that you have in the lab. So please go through that so you know what are the functions are, okay, and what each option would do for you, okay. But so far, it's not going to be too much work, okay, because it's a very simple. You don't need to like have like a crazy settings, okay. So in the lab, what we're going to do is we use the signal generator to have a step function. You don't have a step function in a signal generator, but the closest thing that you have is a square wave. Okay, so we are going to use a square wave with a high duty ratio. So the on time is much larger than the off time. Does that make sense? So basically, in reality, you are going to have such a waveform. It's going to chop. Okay, but we wanted to like maximize the duty ratio. So we can kind of like assume that we have a step function. Okay, remember, if you calculate your time constant, okay, and you already know that you need 5 time constant to reach the final value, okay, the only thing that you need to do is to make sure that the on time of your pulses are more than that 5 time constant. So you know you can reach the final value. Are we good? So how we can do that? Playing with the duty ratio and the frequency of those pulses. So lower frequency, higher duty ratio means wider on time. Are we good? You need to have the on time more than 5 tau. You already could calculate, you already in pre-lab, you already calculated the tau, so you know how much duty time you need, on time you need. Are we good? Now, how to measure the output is simply connect one of these two channels, one of these 4 channels actually, across the capacitor. Now, if you want to have like a two-rule analysis, I suggest to measure both output and input. So you connect one of them to the across the capacitor and another one across your input. So you have two waveforms. One shows how the input is changing, and another one shows how the RC would react to that change. And when you have your pulses, let's say this is the pulse that we have, and this is the response that we are going to get. Okay? We need to first measure the tau. We know what is the definition of the tau. The tau was the time that would takes your output to get to 63% of your final value. Very good. Our final value is not going to be higher than input. It's going to be 99% of that input. It is 1 volt in our slab assignment. So it's going to final value is 0.99. You can assume 1. Okay? It's very close. So what is the 63%? Is going to be 0.63. So when you reach 0.63 volt, let's say here, then your time is going to be 1 tau. Are you good? Now, how to find this? There is an option here named cursor. It gives you 2 sets of cursors. One is horizontal, another one is vertical. Okay? There is a choice here. There is a button here that makes you choose between the horizontal and vertical when you want to set those values. Okay? And for each horizontal and vertical, you have 2 sets of two cursors, A and B, which is shown by the 2 other buttons. So, for example, you choose the horizontal one, and you click on A. Now, this pin would change the position of the A cursor, the horizontal A cursor. And if you push the button for B, now you have control to change the position of the horizontal B cursor. You push to change the horizontal to vertical, and it's the same. It has A and B. Now, my suggestion for you is to use the A, both A as the reference, because you can have and you can see the time 0 in the oscilloscope. Okay, so choose the cursor A, the vertical cursor A. Okay, let me use another color. Choose the vertical cursor A and set it at the time that your change is started. So time 0 in your calculation. Are we good? So this is the vertical A. Now you have another cursor, vertical B. You can move it around until you are at a time that you want. For example, if you wanted to like calculate, you wanted to like measure what is the value of the voltage at time equal to 2 tau, you are going to move this all the way until the value of x of A minus x of B, which is this distance, is equal to that, like, for example, 2 tau. Are we good? Now, as I mentioned, you have another set of cursor. So you have two horizontal one, two. Again, use the horizontal A as a reference value for your voltage. So you would put your horizontal A at the 0 voltage that you see in your waveform. Now you can use the B to move basically between the different values of the voltages. Are we good? Now, how to read using the cursors? If you wanted to like read, for example, 63% of the voltage, you set the horizontal one, you set the horizontal B at a place that YB minus YA, this is B and A, sorry, is going to be that specific voltage that you want. Okay? When you did that, you wanted to see in what time you reach that voltage, right? To measure the time constant. So you set that horizontal B in a way that the difference between the two horizontal is 63% of the final value. Then you change to the vertical one and move the vertical B all the way to the point that both to all the three vertical vertical B, horizontal B, and your waveform cross each other at the same point. Then your XB minus XA will be the time that it takes your waveform to reach the value of YB minus YA. Make sense? Is that clear how to do that? Any question? Any question about that? Now, if you wanted to like do the 2 tau, now you use the vertical one to put the VB, the vertical VB, on the 2 tau. After you reach the 2 tau, now you switch the horizontal one and move the horizontal B to the place that it would intersect with the waveform and the vertical B at the same point, at one point. Then the value between the two horizontal one is going to be the voltage of like 2 tau. Are we good? So this is how you can use the grid.
If tau's at 163, I think 2 tau at like 126.
No,
Okay, no.
no, this is exponential. Okay, it's not linear.
Okay, so you're saying whatever we did that tau was at 0.63, whatever that time is. That,
Yeah.
Okay, this is one.
This is 63% is going to be 1 tau. And here, when you have the 99%, this is going to be 5 tau. Okay. Now, my drawing is not scaled properly. Okay, but this is the definition. Is that clear? The answer?
Yes, it's like 5 tau.
Either that, or when you want to like measure the tau, you are gonna put the horizontal B on the 63%. So the YB horizontal YB minus YA the y value, the y-axis value of minus 8, which is the distance between the two horizontal one, is 63% of the final value. Okay, remember you use the A1 as 0. Okay, so if you move the B all the way up, that the difference is 63%, and then you set the other B in a way that it would cross the vertical B and the waveform at the same point. This is the difference of the x's would be the duration of the time that took your waveform to reach the value of 60. Is that clear? Is it? So this is how you can basically measure the values of your parameter, like in 1 tau, 2 tau, 5 tau, or measure the tau based on the 63% of the final value. Any question? Are we good?
So the towns also don't have a certain, so it's like 60. Not like equal amount of percentage. It's like, say town there is at 1. Oh, 5 towns and 5.
That is exponential. Okay? In 1 tau, you pass this, you reach the 63%. In 1 tau, in 2 tau, maybe like you reach like the 70. Okay, and in 5 tau, all the way in 5 tau, now you reach the 99%. It's not linear, but if you have 2 tau, you have to have 2 times of it. It's exponential. So, very good. Yeah. Any other question? No? Okay. Same kind of like concept goes for the RL circuit. Now, in our RL circuit, in our system, we have parallel RL connection. Let me go toward, this is the same discussion, okay? You run a KCL, KVL, and you would find the function, the exponential function for that first order differential equation. In our assignment, we have a parallel RL, okay, that is a step current, the step function current is injected to those circuits. Now, if you run a KCL, you are going to see that you have the input current equal to the, let's say this is V over R plus, this is the current of the L, which is going to be 1 over L integral of the V dt. Now you can see how it's very similar to the R system. You take a differential, then you would have that the voltage function is going to be proportional to the differential of the voltage. So that means the voltage function is going to be an exponential function. You have your exponential. Is that clear? This is the same mathematical derivation that we went through. If you look at this, if you take a derivative, you are going to have 0 equal to the dv over dt times 1 over R plus 1 over L V. So dv over dt is going to be minus R over L V. That means your tau is going to be minus L over R. Not minus L over R. And you would have an exponential function, e to the power of minus t over tau. So this is basically is going to be the same. The calculation, the derivation is going to be the same as RC that we talked about. Okay, and you already have that in calculus and second one. So you run a KCL, you find the value of the V, but this is not the parameter that you want to like have. Your parameter is current of the L. Remember, the current of the L, this function that you find is the voltage across the L. So you need to take an integral to find the current. And then you have your final function that you can put the times that you need in that function and find the values. Are we good? In the experiment, since we don't have a current source, we are going to use a voltage, a step voltage, instead of the step current. So the values that you are going to see in the measurements are going to be different than the values in calculation. Okay? Find out the error and try to discuss that. What's the difference and how you can justify that difference. The reason is because we have a current source in a calculation, a voltage source in a actual measure, lab measurement. Okay, but I want you to like think about it and find out, okay, why this change did and resulted in that error. Very good. Now, using the oscilloscope to measure the RL, okay, the current of the inductor is not as easy. Again, the oscilloscope only measures the voltage. The value that we want is current. How we can fix that? How we can measure the current of the inductor when oscilloscope cannot detect the current? Anyone has any idea? Voltage of the inductor should be pretty very regular. Okay, so probably you will not be. There is not in reality. There is going to be a voltage, but it's not going to be easy to. Okay, so you want to. No, no. You don't have any frequency change in your circuit. Now, you wanted to like measure the current, but you can. But the tool you have is detect the voltage. So what you have to do is to change the current to the voltage. How we can easily change the current to the voltage? What component would change the current to the voltage without adding a nonlinear dynamic or a differential integral dynamic? So you are going to put in a small resistor in series with your inductor, and you are going to measure the voltage across that resistor. Let's say this resistor is 10 ohm. Okay? Then whatever voltage you measure across this resistor is going to be 10 times of the current of the inductor. Is that clear? So you make a measurement. Let's say you measured like a 10 volt. That means your current is 1 amp if your resistor is 10. Is that clear? How to do that? So this is the trick that you need to do in order to be able to like measure the current of your inductor. Any question? Now, finding the tau or the value of the current in 1 tau, 2 tau, all the way to 5 tau is exactly the same. The process is exactly the same as we discussed in RC. So you use those cursors to tune the position of those two sets of cursor and then read the values. Are we okay? Are we good? Now, when you have in the last system, we have an RLC. Now we have two components that has a differential integral dynamic. That means we have a second order circuit. Okay? The second order circuit, if you run a KVL, you are going to find this is a Laplace transform of that second order Like a transfer function of that second order. You familiar with transfer function and Laplace transform? Anyone have problem with that? This is each differential, each level of differential is one s. So s squared is the second order differential of that problem. Okay, now when you have a standard second order transfer function, which is the standard second order differential equation, this is going to be x double dot plus the psi omega n. This is another way that to show that x dot plus omega n square x equal to 0. This is also a standard way. Same. This is the same. Okay. This is the standard way to show the second order differential equation in math. Okay. If you run a KVL, you are going to see such a function. You have to change it to make it a standard by making the coefficients of the x double dot, the second order, equal to 1. So if you wanted to like multiply by any variable or divide by any variable, you have to do it for all the terms. So you make these coefficients of the x double dot equal to 1. Now that you have that, whatever is the coefficients of x or whatever parameter that you have, it could be voltage or current, is going to be the square root of natural frequency. Okay, I am using this term. I really hope that you remember that from the calculus and circuit board. If you don't, please let me know. No? Okay. And whatever is as a coefficient that you have in front of x dot is going to be your decay rate. What we have in our assignment is to find the oscillation frequency, not natural frequency. Oscillation frequency, okay, decay rate, and the peak voltage. Okay, now, if you analyze that second order circuit that I gave you, this is a standard second order circuit. You just have to like replace, you run a KVL and replace psi omega n by these values RLC, and also omega n squared by values RLC. If you do that, you would find out that the omega n or omega 0, which is the natural frequency, is going to be 1 over a square root of LC. Okay? And the decay rate is going to be 1 over 2R. You run your derivation and you would find that. So you have the decay rate and you have the natural frequency. The function that we saw when you wanted to like find how is the oscillation for frequency of oscillation, you have to find the zeros of that function. Hopefully you remember from the transfer function that the zeros of the function would define the oscillation frequency, the poles of our transfer function, the system, the oscillation frequency. For that specific equation, the zeros are going to be this. The minus alpha, which is that psi omega n, plus minus, you can say omega n, psi squared minus 1. These are the same, okay? I'm just using two indexes, two different indexes, okay? So, you have the decay rate by using the definition that we had. Whatever happens here is going to be your oscillation frequency. So what is the oscillation frequency? Natural frequency times square root of psi squared minus 1, or a square root of alpha squared minus natural frequency squared. either way. So this is going to be your oscillation frequency. This is decay rate. Forget about the -1. It is the absolute value that importance. The alpha is decay rate. This term is oscillation frequency. Are we good? Now, depend on what would be the value of psi, which means what would be the value of alpha. If your alpha is bigger than omega 0 or omega n, the value under the square root is going to be positive. All right? So we are going to have two s's, two zeros, both of them are real. We call this overdamp. If those two are equal to each other, the square root becomes 0. So both of the zeros are going to be equal to each other, equal to the minus alpha. So you have two real repeated zeros. We call this critically damped. And if you have alpha less than omega 0, which if you wanted to define it by psi, this is psi bigger than 1, this is psi less than 1, and this is psi equal to 1. Okay, this is the same. If you have alpha less than omega, then underneath this square root, you have a negative number, which means an imaginary. Your zeros are going to be two complex numbers which are conjugate of each other. So whatever is the value of the imaginary number is going to be your oscillation frequency. Remember that? So that's why we call this second term oscillation frequency. Are we good? Now, your circuit is going to be under that. So you are going to have an oscillation frequency. The formula for oscillation frequency, that x of t is going to be e to the power of minus psi omega n t times a times cosine of the omega d. We call this oscillation frequency omega d. Okay? Times t plus b times sine of omega d times t. This is the general solution to that standard second order differential equation when you have an underdamped situation. You put initial condition to find what is the value of the A and B, and like an infinite time or like a pi over 2 time, okay? The value of the time equal to pi over 2. So based on those values, you can find your A and B, which if you do that, A is going to be 0. I'm going to give you like a hint. A is going to be 0 and B is going to be 1 for our situation. So what you're going to end up is that whatever variable that you have in your second order equation, I'm not sure this is a current or voltage. You have to find it. Whatever variable you have here, okay, is going to be e to the power of minus psi omega n times sine of omega dt. This is going to be your function. Now, when that function reaches the peak, when the differential of that function is equal to 0. So you need to differentiate that function, make it equal to 0, and find out what time satisfies that condition, the differential equal to 0. That time is going to be the time of peak in you put the time of peak inside your original voltage or current, then you have the value for the peak value of that function. Is that clear? What we done? Any question about that? For measurement, you simply instruct the circuit. You have a step function. The output is the voltage across the resistor, so you can connect the oscilloscope to across the resistor, and you are gonna find such an oscillation, okay? Such an oscillation. So the oscillation frequency is 1 over the time that it takes the waveform to finish one cycle. The decay rate is the time that it takes the waveform to go from the peak value all the way to the 63% of peak value. Okay, I already put that in the lab assignment, the hint. And the peak value is easy to measure. It's just there. No, please see please. 33. It's kind of like close to 63 chain. Okay, so we fall 63%, around 63% from the initial value to open. Now, I am going to move a little bit fast because you have a simulation to do too. When you open up the multisim, this is when you push the new button, this is what you want to see. Okay? In the menu place, you have option component. This is where you can find your component. When you click on that, in the menu group, you have all the categories of components. The resistance, capacitor, and inductor are in the basic menu. Okay, so you choose that. When you choose that, it opens up the family inside the basic group. When you want to, like, for example, choose your resistor, you select the resistor, you select the value that you want, click OK, and then you could insert your value. Same goes for the capacitor and inductor. Are we clear? So you can choose your values. For the sources, we want the step function. So you choose the group source, and in the group source, you have signal voltage source and signal current source. For RC and RLC, we had voltage source. For RL, we had current source. So you choose the signal voltage source, and here, where is that? You have the step voltage. Is that clear? Same goes for the current. You choose the current source, you have the step current. Okay? If you run those placement, you are going to see you have to create such a circuit. This is RC, you just put in the component. And the source, RC, and the source, RC, and the source. Double click on the source and put the initial condition as 0, all of them. Okay? Because we want to start from 0. There is another value that is a time that you want the step function to rise from 0 to final value. You can't put that instantly. So 0 is not enough. Okay? With a simulation, it would create a problem with the numerical solutions. Okay? What you have to do is to put a very, very tiny number. I put 1 nano. So you put 1 nano, so it would start from 0, and in 1 nanosecond, it gets to the high voltage. So you have your step function. Are we clear? For all the values, all the sources, both voltage and current. Is that clear? Now, when you did that, you click on the simulate menu. In the simulate menu, you have an analysis and simulation option. You click on that. This window will open. Okay? We want to run a transient analysis, so we choose the transient. Okay? You have several pages here. In the page output, in the tab output, you have to add whatever value that you wanted to measure. It could be the current of the inductor or the voltage across a resistor. There is a name for that voltage. Okay, if you double click on the wires, you can see what is the node's name. Okay, so for example, if you double click on this wire, in this circuit that I draw, this wire is the second node. So when I wanted to like see the voltage across capacitor, I choose V2. Are we good? When you chose that, you set in the analysis parameter, you set the values of start time and final time and end time for your simulation and hit run. Are we good? In all the system are the same. You just need to change the output. So here you remove what exists for the next circuit and add the new output that you wanted to see. And that way you can run your simulation. And if you run the simulation, it would give you the waveform of that specific parameter that you chose for out. It should be the same waveform that you see in oscilloscope, which you already know how to find the tau is a 63% of the final value, and how to find the values for 1 tau, 2 tau, 5 tau. You know what I'm saying? So same goes for the RL and RLC. Is that clear? Any question? No? Are we good? Okay, thank you very much. If you have any question, please send me an email or ask the TAs in the lab so we can help you to run the experiment. Oh, before you go, I wanted to like mention